Hello everybody, welcome to this video on graphical solution to linear programming problems. Today we will go over the graphical solution. In this video we're going to go over the graphical solution to the first problem that we did last week, which was the furniture problem. I have the problem right here on the screen. This is the object. The objective is to maximize 7t plus 5c, which was the profit function, subject to the two constraints. This was the carpentry constraint and this was the painting constraint, and we also have the non-negativity constraint. Now technically we also have the integer constraint, but we are going to ignore that for the time being. Right, so I will do the graphical solution right here. Now usually I would do this on the whiteboard and you'd follow along with me, but either case, so you can do this using a pencil and paper or a pen and paper. Either way is fine. And when you, as you will see, I'm not drawing straight lines exactly, so as long as the lines are straight enough, it's usually okay, right? So let's so what exactly is the graphical solution? What is the idea behind it? So the graphical solution to a linear programming problem takes advantage of the fact that smaller problems have two variables. So we can take the two variables, represent one of the variables on the x-axis, another variable on the y-axis, and solve the problem using some on the coordinate plane, right? So you can have a y-axis and x-axis, and you can have the four quadrants, and you can look at the four quadrants, look at the constraints that we have, and then figure out what the solution is. So that's the procedure that we're going to go over. That's the idea behind the graphical solution. Right. So like I said, this only works for problems that have two variables only. Okay. So in this case, the two variables are t and c for tables and chairs. So what I'm going to do is I'm going to draw the x and the y-axis and then take it from there. Now the first thing I want you to notice is that we have the non-negativity constraint. So non-negativity means that both the number of tables and the number of chairs should be both positive or zero at worst. They can't be negative numbers, which doesn't make sense. So because that's the case, we don't have to consider all four. We don't have to consider all four quadrants. So when you draw a coordinate plane, you have four quadrants. You have the first quadrant, second quadrant, the third quadrant, and the fourth quadrant, right? We don't have to consider the second quadrant because here the value of x is negative. We don't have to consider this quadrant because the value of x and y are both negative, and here x is positive but y is negative. So the only quadrant that we need to consider is the first quadrant. So all our solutions is going to be in the first quadrant. So what I'm going to do is I'm going to erase all of this and just draw the first quadrant out, right? So let me do that. So let's go back to the first quadrant. So I'm just going to draw x-axis like this. Yes, it's not exactly straight, and that's okay. Right. So I'm going to represent this as the t-axis for tables, and this is the c-axis for chairs. Right. So what I want to do is I want to represent my two constraints. So we're always going to begin the graphical solution problem with the constraints. Maybe you know what? Let me just start this on a different sheet altogether. Let me start it here. So that's the t-axis and that's the c-axis, right? So this is 0, 0, 0 tables and 0 chairs, right? So let's begin. So we're going to begin with the first thing that we need to figure out is first thing that we're going to do is we're going to take the constraints, and then using the constraints we're going to figure out all the points, all the values of tables and all the combinations of tables and chairs which satisfy all the constraints that we have. So we want to see which combinations of tables and chairs satisfy these constraints. Now, what does that mean? It means that, for example, we know for a fact that we cannot make 1,000 tables and 1,000 chairs, right? Because 1,000 tables and 1,000 chairs require a lot of carpentry time and a lot of painting time, which is way more than what we have available, or for the 10,000 chairs and 10,000 tables. So there's some sort of constraint on the number of tables and chairs that they can make. The first thing that we're going to do is we're going to look at the two constraints that we have and see what are the combinations of tables and chairs that are feasible. That's the word that we're going to use. It's called feasible. So step one is find the feasible region. You can call it the feasible region. So the feasible region is the set of all points which satisfy all the constraints that we have, right? So that's the first step. So for us to find this set of all points, to find the feasible region, we first need to know how to represent this inequality here on the XY, on the TC plane, and this inequality here on the TC plane. Once we have that, then we can figure out which points satisfy both inequalities, and then we are good, right? So let's begin with the first inequality. Whenever you want to represent an inequality on a two-dimensional plane like this, we always begin with the corresponding equation. So what we'll do is to figure out how to represent this, we'll first start with the equation. So that is 3 times t plus 4 times c is equal to 2400, right? So it's a corresponding equation, and any equation like this on a two-dimensional plane like this is a straight line. So we're going to draw this straight line, and then using the straight line we're going to figure out the inequality. So how do I draw a straight line? To draw a straight line I need any 2 points. So I can figure out any 2 points, join the 2 points, and then I can extend the points, and I have the straight line. But the simplest points to find are the 2 points where the straight line meets the x-axis and the y-axis. In this case, where the straight line meets the t-axis and the c-axis. So how do I find that? Simple. We start by setting t equal to 0. So in this equation, if I set t is equal to 0, that is the point where it meets the c-axis. So if t is equal to 0, then c is equal to, so if I plug in t is equal to 0, I get 4 times c is equal to 2400, or c is equal to 600, right? So that's the point where the straight line meets the c-axis. Similarly, if I set c is equal to 0, if I set c is equal to 0, the value of t is going to be, if I set c is equal to 0, I get 3 times t is 2400, or t is equal to 800, right? So 800 comma 0 is the point where it meets the x-axis. 0 comma 600 is the point where it meets the y-axis. So here, let me try to make this better. That's good enough, right? So let's say this is 200, it's 400, that's 600, that's 800, right? So on the x-axis it is 800 comma 0, again 800 comma 0 here, 800. Well, it's not the x-axis, it's a t-axis, I'm sorry, and this is the c-axis. So 800 comma 0 is the point here on the x-axis. On the t-axis, on the c-axis, it is 0 comma 600. Let's say 200, 400, and 600. It's definitely not to scale, but it's approximately to scale, and then that's good enough. But so that's our straight line. So this is a straight line that joins 0 comma 600 to 800 comma 0, right? Right. It's not any better, but okay. So now what is this? So this is the straight line corresponding to this inequality here, but I want to represent the inequality. How is the straight line going to help me? So I start with the straight line and then I say, okay, this straight line, I can extend it all the way to infinity to this side. I can extend it all the way to infinity to this side. So this straight line divides this quadrant into two regions. There is one region on this side and there's another region on this side. And each of these regions represents one of the inequalities. One of these regions is going to be less than, and another region is going to be greater than. What that means is that all points on one side of the straight line will be such that 3t plus 4c will be greater than or equal to 2400, and all points on another side will be such that 3t plus 4c is less than or equal to 2400. Now how do I figure out which side is which? Well, it's simple. Take any point on one side, plug it into the inequality and see if it satisfies the inequality. So we begin. We take the point 0, 0, and then we plug this into this inequality right here. So we take 0, 0. If we plug it into the inequality, we get 3 times 0 plus 4 times 0, which is all 0. So 0 is less than 2400. So 0, 0 satisfies the inequality, which means that all points on this side of the straight line satisfy this inequality. Which means that our final solution can only be here in this region right here. It can only be in this region. Why? Because all points on this side are such that 3t plus 4c is greater than 2400, which means that you need more than 2400 hours of carpentry time to make those combinations of tables and chairs, which means that we cannot use that, right? So that's the first inequality. Now similarly, let's figure out the second inequality. Let's begin here. So let's take the other inequality. So you get 2 times t plus c is less than or equal to 1000. So we'll begin with equal to 1000. We'll begin with the straight line, and we'll similarly figure out the points where it meets the x and the y axis. So if I plug in t is equal to 0, I'm going to get c is equal to 1000. And if I plug in c is equal to 0, I'm going to get t is equal to 500. Okay, so I had to take a small break. Sorry about that. Right. So the endpoints for the equation 2t plus c is equal to 1000 are t is equal to 0 and c is 1000. And then when c is equal to 0, t is 500. So because we are taking t as the x-axis and c as the y-axis, this is 0, 1000 and 500, 0. So let's mark them on the graph here. Okay. So it'll be 0, 1000 first. So if this is 600, let's say this is 800, and this is 1000. So that's 0, 1000 right there. And then the other one, 0, 1000, and then 500, 0. So this is 800, this is 600, that's 400, 500 is right there. That's 500, 0. Sorry about that. Right there. Then we can join these 2 points. There you go. This is the straight line. And again, similar to what we were talking about before, for this this straight line here, so that equation here is a straight line. the straight line divides the space into two regions. One side will be less than or equal to, the other side will be greater than or equal to, and we can figure it out the same way. So if you take 0, 0 and plug it into the equation, we will get 0 plus 0, 0 is less than 1000, which means that 0, 0 is on the side of less than or equal to side of the constraint. So this is the less than or equal to side. So let's say that I okay, right? So this is the side of this is the inequality 2t plus c is less than or equal to 1000. So we have the two inequalities. This is 3t plus 4c is less than 2400 right here, and 2t plus c is less than 1000 right here. So all of the points within this region that I shaded blue, all of these points are such that if you multiply 2 times the value of t and add the value of c, that value is less than 1000, right? And the same goes here. All the points here are such that 3t plus 4c is less than 2400. So the points that satisfy both the inequalities are the points within this quadrilateral right here. So let me mark that. So this quadrilateral right here, this quadrilateral right here, this is the one that represents the feasible regions. Like we said, feasible region is the region of space where the points satisfy all the constraints of a linear programming problem. So this here is the feasible region, which is common to both of the regions right there. So our final solution is going to be one of the points within this region. And that's important for us to know, right? Now, there are an infinite number of points within this region, but we need to figure out which is the best point, and that's the next step that we're going to take. Okay, so this is how you find the feasible region. Plot all the constraints. So sometimes in this case, both constraints were less than or equal to. Sometimes you can have greater than or equal to constraints. Sometimes you can just have equal to constraints. So all of that, you plot all of them, you find the region where all the constraints meet. So sometimes what happens is that some constraints could be contradictory. If that's the case, then you cannot solve this problem. But in most cases, constraints don't tend to be contradictory. They tend to be complementary, in which case you'll find the feasible region, and then using the feasible region, you're going to find the optimal solution. But how do you find the optimal solution? So that's the important piece to understand here. So the optimal solution is based off of the objective function. So let's look at the objective function. Oops, I'm sorry. So the objective function objective is to maximize 7t plus 5c. So of all of the infinite number of points here, we want to find the point that finds the maximum value of 7 times t plus 5 times c. Now, there is no reason why there has to be a single point. There could be multiple points which do that, but we want to be able to find at least one of those points. Now, how do we do that? Well, technically speaking, we have to take every one of these points, plug them in to the objective function and find which minimizes it. But like we said before, there are an infinite number of points here. So how do we go about it? Well, there is this fundamental theorem of linear programming which says that the final solution to any linear programming problem can be found not within the feasible region, but at one of the endpoints of the feasible region. So you take one of the endpoints of the feasible region. I think this is a glitter pencil. Anyway, so one of these endpoints. So each feasible region will be either a triangle or a quadrilateral or a pentagon or a hexagon, depending upon how many constraints you have and how the lines cross each other, right? So it will be some sort of polygon. So you take the end points of the polygon and your final solution will be only one of those points. It won't be any of the interior points. Now, why is that? So simple example, let's say that you say that the final solution is here, which means that, so let's say that I say the final solution here. So this is the point, which is, let's say 400 on the y-axis and 200 on the x-axis, right? That's the point. Let's say that the final solution, somehow I say that the final solution is here, but I can always keep the y-axis, the x-axis the same at 200 and increase the value of y-axis so that it reaches the end point. So let's say that I go here and let's say that that is, for the sake of argument, 500. So 200 comma 500 is a better solution than 200 comma 400 because 200 comma 500 will give us a larger value of the objective function. So this solution says make 200 tables and 400 chairs. This solution says make 200 tables and 500 chairs. So this is definitely a much better solution because this will give us a larger profit, right? Now, in a similar vein, you can show that these endpoints here give us better solutions than any points on the straight line itself. Either this will be better or this will be better. So we can keep repeating that argument and show that if you take any point inside, there is always going to be a point on the edge of the polygon which is better. And we can also show that when you take points on the edges, the end points are always going to be better than the points on the edges, right? Okay, so with that calculation done, one of these 4 endpoints is going to be the final solution. So we know this point is 0, 0. Now this we can obviously exclude because 0, 0 is not going to be the final solution. And the reason for that is obviously if you don't make any chairs and tables, you won't make any profit. So any other solution is obviously better than that. So the potential solutions we are considering are these 3 points. So we have 0, 600. So let me name the points. I'm going to name this point X. I'm going to name this point Y. And I'm going to name this point Z, right? So point X, 0, 600, point Z is 500, 0. So let me make a table here. I'm going to make a table. So this is this point Y. We don't know point Y yet. We'll come to that. This is the point. This is the potential solution. This is the potential solution. This is the value of the objective function. So this is the value of the objective function. So which means that if my solution is 0, 600, which means this says that don't make any tables, make 600 chairs. This solution says make only 500 tables, don't make any chairs. And this solution here will be a combination of chairs and tables because it's obviously not on the x-axis or the y-axis. We don't know what that point is just yet. So let's find that point. So how do I find what this point is? So one thing that I don't want you to do is guess the point. If you guess the point, you will get it wrong. And if you get it wrong, your solution might be wrong. So do not guess the point. And I will be looking for you to do the actual calculation to find the point. So this point here is the point of intersection of these 2 straight lines. So we have one straight line here and we have another straight line here. So the point of intersection of these 2 straight lines is this point here. So let's find that out. So I'm going to make a let me insert another text box here. So the 2 straight lines are 3t plus c 2400 and 2t plus c is 1000. We have to find the point of intersection of both of these straight lines. Now, how do we do that? Well, to do that, so how do we find the point of intersection? So point of intersection, there are multiple ways of doing it. You can solve this equation for c. So you can say that c is 1000 minus 2t, and then plug that, oh, that's 3 times 8 times 8, and plug that into this equation here. So you say c is 1000 minus 2t, plug it in here and solve for t. That's one way of doing it. The other way of doing it is to solve them as simultaneous equations. Now, how do we do that? For solving the simultaneous equations, you take 3t plus 4 times c is equal to 2400, right? So that's one equation. The other equation is 2 times t plus c is equal to 1000. That's the other equation. So I am going to get rid of one of the variables by multiplying and subtracting and things like that. So you have done this in algebra before, right? So what I'm going to do is I'm going to take this whole equation, multiply it with 4. The reason I'm multiplying it with 4 is that the coefficient of c will be 4 and 4, and then I'm going to subtract it. So essentially I'm saying I'm going to multiply it with minus 4 here. I'm going to multiply it with minus 4 and add both of the equations, right? What do I end up with? So if you multiply the equation, so it's going to be 3 times t minus 8 times c, right? 3 times c minus 8 times c is minus 5 times t is equal to 2400 minus 4000. So that will be 2400 minus 4000 will be minus 1600, right? And then this implies that if I divide both sides of the equation with minus 5, this will give me t is equal to, how much is 1600 divided by 5? 320. So this will give me t is equal to 320. So I take the two equations, multiply the second equation with minus 4, add the two equations. I'll end up with only t. So we are eliminating one of the variables by matching coefficients and then adding or subtracting depending upon what we need to do. And using that, we found one of the variables. Now we'll take the value of this variable and plug it into one of these equations and find the value of the other variable. Because it's the point of intersection, the point of intersection will be a single point. So it will satisfy both equations. Okay, so let's find the other point. So I'm going to take t is 320 and plug it into the second equation because that's easier. So that'll give me 2 times 320 plus c is equal to 1000. This will imply, so 2 times 320 is 640. So c 640 minus, let's do that. Which implies I can subtract 640 from, oops, that's 1000. Can subtract 640 from both sides, and that'll give me c is equal to 360, right? 360. So that is the point of intersection of the two straight lines which bound these inequalities, right? Go back. Let me go back here. So this point here is the x-axis is 300 and, I'm sorry, the x is 300, so t is 320, c is 360. So this point right here is 320, 360. Right there. 320, 360. Right there. So you could not have guessed that because we are not drawing everything perfectly to scale. So you could not have guessed that this is the value. So if you had guessed, you'd probably end up guessing something like 400, 400 or something like that. And that is obviously not the point of intersection. So that is my second point that I'm considering for my potential solution, 320, 360, right? So I'm finding the potential solution. So these are my three options. Just making chairs, you'll make 600 chairs. Just making tables, you'll make 500 tables. Or you can make a combination of 320 and 360. So what's the final answer? Now the obvious inclination is to say that point Y is the final solution, because that has a combination of chairs and tables, while the other solutions do not have a combination of chairs and tables. And you will be wrong. You cannot choose the final solution based upon a gut feeling. The final solution is based purely on the value of the objective function. So the objective function might be such that, say for example, if the profit from tables is so much more than the profit from chairs, it might make sense for you to just make tables. And the same goes the other way. If the profit from chairs is so much more than the profit from tables, then it might make sense for you to just make chairs and no tables. So these solutions could also be the final answer. You don't know that. And how do we find the final answer? We use the objective function, 7 times t plus 5 times c. So the objective function is 7 times t plus 5 times c, right? So let's take this objective function, plug in the values, and figure out which of these combinations of chairs and tables give us the maximum profit. So let's do that. So if I plug in t is equal to 0, c is equal to 600, that will give me $3,000. So that's my profit. So I take the objective function. So 7 times 0 plus 5 times 600. So I take this and plug it into this equation. So it'll give me $3,000. So 7 times 0 plus 5 times 600, right? Now let's do the other end, which is 7 times 500, then 5 times 0. 7 times 500, so that'll be $3,500. Right? Now let's do the other one. Get rid of this dollar sign completely. And the final solution here will be 7 times 320 plus 5 times 360, which I can calculate here. 7 times 320 plus 5 times 360. Oops. That will give me 4,040, right? 7 times 320 plus 5 times 360. That will give me 4,040. Right? And that is the final solution. So that's the profit here. So if I make 320 tables and 360 chairs, it's going to give me a profit of 4,040. If I just make 600 chairs, it's going to give me a profit of 3,000. If I just make 500 chairs, it gives me a profit of 3,500. So of all of these values, Y gives me the maximum profit. So that's the one that I'm going to choose. So Y is my optimal solution right here. That's my optimal solution. So the optimal solution, there are two parts. So we say that the final solution is based upon all the constraints, the painting constraint and the carpentry constraint. The optimal solution to this problem is make 320 tables and 360 chairs, and you'll make a profit of $4,040 for the month. And that's the per week, 4,040 per week. And that's the final solution, right? And this is how you do the graphical method. So you find the endpoint. So you always start by finding the endpoints. I'll just move that here. After you find the endpoint, you find the point of intersection, if need be. So sometimes you might have to find one point of intersection. Sometimes you might have to find multiple points of intersection. Either way, so you find points of intersection and you're essentially finding the end points of the feasible region. So let's say that there was another straight line like this and there was a point of intersection here that was not part of the feasible region. Then you don't have to find that. Just identify the end points of the feasible region, the region where all constraints meet, right? So these are the set of points which satisfy all your constraints. So find the end points of the feasible region and you plug those endpoints into the objective function, and see which gives you the maximum solution, right? And that is the graphical method. Okay. Thank you.